Hi, welcome to this online talk on physics of language models, part 4.1, architecture design and the magic of canon layers. So since many of you know that this is a paper with so many results, I decided to further divide the talk into two parts. 4.1a, which is this talk, that will cover why real-life pretraining is noisy and how to build a versatile synthetic pretraining playground. In the next talk that will be online tomorrow, I will cover once you have this playground, then what architectural principles can you derive from it? And in particular, what are the so-called canon layers that will be introduced to improve the model's reasoning and so on. So if you're a theoretician or methodologist, you will find this particular talk very interesting. And to me, this is actually the most interesting part of this entire paper, because if you build a very bad synthetic playground, then maybe you are not going to derive very meaningful architecture principles. But if you build the one that's powerful enough, then that can help you to use very small scale pretraining to predict what real-life pretraining will behave. So this is something that I think most the methodologists will enjoy. And the second talk is more for applied researchers, in particular, once you have this playground, once you believe that the playground is well established, then what architecture insights can you derive from it, right? If you care about how to build the model of tomorrow better in terms of how deep, for instance, it can reason, then you can directly jump to the second talk, and I'm going to tell you the answer directly without the methodology part. So this first talk is about the methodology. All right, so this talk is about the language model architecture research, right? And how does a typical kind of architecture research look like, right? You pre-train a model, of course, and then you try to evaluate it. And typically when people try to evaluate it, you use a zero-shot performance benchmarks. And for instance, you can use the so-called LM Evolve toolkit to help you evaluate the model in some common sense reasoning tasks. So the following table is something that you can find very common, I think, in every single architecture research paper. That is, there are especially 8 very important real-life benchmarks: the Lambda dataset, the PCA, the Hallerswalk, the Winograd, the ArcEasy, ArcChallenge, CCA, and the BoolQ. So that once you pre-train the model and evaluate them on those benchmarks, and suppose you are lucky enough that your newly designed architecture is better than all the prior works in all of the scales that you tested, then you're happy and you can write a paper and publish at ISML, for instance. So this is essentially how most of the recent advances in architecture design papers look like. So here, one particular thing I want to highlight here, which is this largest scale that almost all of those papers took, that is to pre-train a 1.3 billion parameter model using 100 billion pre-trained tokens. So I want to give a name to this. That is, I call this academic scale pre-training. Okay, so on one hand, this pre-training is sort of large enough. By the way, 1.3 billion parameters really means, for instance, if it's a transformer, that's 24 layers and 2,000 dimensions. And the 100 billion tokens will be already sufficient enough for you to train a model that can speak basic English, for instance, to answer some Wikipedia questions. So this is already taking, say, $1,000 the minimal for you to pre-train. So I'm calling this academic scale because in academia typically we're found limited, and how can you repeat experiments like this too many times, right? But in fact, even in industry, right, in industry research labs such as NVIDIA Research, where they publish the gated delta net, or even Google Research, or even FAIR at Meta, when my colleagues, for instance, studied the multi-token attention, this also turns out to be the largest scale we can run. For obvious reason, right? You don't want to spend when doing architecture research, you want to repeat the experiments many times by tuning parameters and so on, but you typically are constrained by budgets. You cannot redo this experiment too many times if the scale is too large. So this is a particular scale I want to focus on in today's talk. And in this scale, let's see what do people already know. And in particular, people typically pre-train the model on a specific data set, right? And one of them, very famous one, is the so-called fine web EDU data set. And if you pre-train the model on that, For instance, if you take the transformer architecture, then this is the average score, for instance, among the 8 benchmark evaluations of the transformer model. And throughout today's talk, whenever I say transformer, I actually mean the original decoder-only like transformer, but adding 2 enhancements. One is the rope, the rotary position embedding. The other one is the gated MLP, also known as like SWIGLU. So this is also referred to by some authors as Transformer++, and some people call it Llama because it was the Llama 1 team who actually popularized this specific choice. And in today's talk, I may also call it rope, just to emphasize that it's using this rotary embedding. But whatever the name means, then throughout today's talk, I may interchangeably use like transformer or llama or rope to actually mean the same thing. So that's like the transformer's performance reported in the GDM paper and the Atlas paper from Google, for instance. And 2 other architectures I want to specifically highlight in today and tomorrow's talk is this Mamba2 architecture and this gated delta net or GDN architectures. So these 2 are no longer transformers. They are linear time models comparing to transformers, and they are actually the 2 models that have been currently like used by those open source like frontier labs. For instance, NVIDIA's Nemotron architecture is using Mamba2 in their hybrid design, and Kwon and actually Kimi as well are using the GDM model as their linear model design. So there is actually a reason that the frontier labs are picking those 2 architectures to hybrid it with transformer. It's because those 2 architectures actually perform better than transformer even on those like reported benchmarks. So this is really some great news, right? So people have designed better architectures than transformers and also like used in practice by frontier labs, even to the 70 billion scale. So this is what's already being done like in practice. But one critical thing that you opened up like a research paper in this field is that those numbers are not really very static. So if you open another paper, you may find out that the transformers can actually perform 1% better in terms of the accuracy, for instance, reported in Google's paper, right? So therefore, like a very crucial question to ask is regarding this like accuracy gain of maybe 2 or 3%. Like, how real is it? And if you like tune the parameters a bit better, can you like maybe like shrink kind of the gap across architectures, right? So I myself like used to work in the field of optimization, right? So I was maybe a little bit overconfident. I thought the first time I saw this table, I thought, well, can I maybe tune the parameters a little bit better? So I did the following. That is, I took a different set of parameters. I decreased the batch size that were used by those papers, and I also increased the learning rates. So here, like I tuned and picked the 2 of the best learning rates and say that I plot the maximum of the 2 accuracies. You can also do the minimum, but the results will be similar. And here's what I found out. If you use like my choice of the parameters, you can get actually a lot better than all the reported accuracies above for the same data set, the same fine web EDO data set. And what is very reassuring to know is that even after my like very careful comparison, by the way, like I'm also controlling the data shuffling seeds. So I made sure like all the 3 models are pre-trained, using the same data and also the same data shuffling so that they really see the same data in the same order. So the very reassuring thing to know is that once you do things like very carefully and best tune the parameters and pick, say, the max out of the 2, so you stabilize the comparison even better, you still see this performance gain, right? So Mamba2 and GDN still like outperform Llama. So this is very great. And now like let me tell you a real one-line magic. That is, I have a very secret way to even outperform Mamba and GDN. Okay, so this is a one-line magic, and if anything you want to take from today's talk, this is the place. That is, the number 1 magic I can do is to change the random seed to 21. The number 2 magic I can do is to change the random seed to 24. So in fact, I tested like 8 different random seeds, and I noticed that just by changing the model's initialization seed, I'm not changing the data's random seed, I'm just changing the model's initialization seeds. This can already make the accuracy like change by really a lot. And for instance, you can even make Llama to have an average accuracy that even outperform Mamba 2 and the GDN. So I did this experiment at the beginning of this year, and this really drives me crazy, right? So I want to understand, for instance, how much does the model's random seed really impact their performance on those standard real-life benchmarks. So here is the experiment. I tried 8 different seeds by, in the first 8 rows, I vary both the model's random seeds and as well as the data's random seeds. But in the next 8 rows, I only vary the model's random seeds, but keeping the data's random seeds fixed. Okay, so in these 2 ways, in both of them, I noticed that the model could have a really large variance in terms of their evaluation benchmarks. And for instance, the very famous like ArcEasy and ArcChallenge, you can even see like a 2 or 3% variation, on those 2 benchmarks. And on the Lambda dataset, the Lambda evaluation benchmark, you can see an even larger difference. And if you recall from the previous slide, actually the advantage of using GDN or /Mamba over Llama or over Transformer was actually only smaller than this variation. So therefore, if you think about it, the architectural differences are really lost in noise. So if you vary the models, say data seeds or maybe models initialization seeds by 8 different possibilities, you see like a difference of between 2 and 4% of change in a benchmark. But if you compare 2 architectures, the difference is only 1 to 2%. Then it's not convincing to me that maybe GDN or /Mamba are better than Llama, right? So maybe like all of the discoveries you have found are actually buried by this noise from the random seeds. So this is like for most of the benchmarks, but some of the benchmarks are better. So for instance, Halaswag that people really like in practice because it's a larger evaluation suite. So therefore, like it's more stable. So you only observe like 0.8% difference. But unfortunately, the advantage of using, say, Mamba over Llama is only 0.4%. So therefore, like it's still like buried in noise. So those are the so-called discriminative tasks. So those are very nice in the sense that those are multi-choice questions. So after pre-training a model, you give it some context, and then you can supply it. After the context, you can give it one of the 4 multiple choice answers and see like which answer does the model prefer. So this is actually the way to evaluate the model by just looking at the cross entropy loss on the 4 choices and see which one is the biggest. So that's like the model's preference among the 4 answers, and then you can compare that to the true answer. So this is like how people evaluate the model, in those at least one of those 8 benchmarks. So this is known as discriminative tasks. But people also evaluate the model in different ways. And another particular way is the so-called perplexity, also known as the training loss or cross-entropy loss with respect to a dataset. But people really hate to use perplexity as a way to evaluate a model because perplexity more captures how much the model memorizes the dataset. So for instance, if it's the Wikipedia dataset, then you see that all the models memorize it maybe to almost the same kind of level of correctness. This is believable just because Wikipedia is really like repeated a lot of times in the pre-training data, regardless of which pre-trained data suite you use. It can be FileWeb, EDU, or it can be Sling Pajama, but Wikipedia is always there. And if you use like some other data set, maybe like use that's not really very abundant in the pre-trained data set, and you evaluate its perplexity, maybe like you're going to see a larger variance. So overall, like people really don't like to use perplexity, like it doesn't capture, like, for instance, the model's reasoning capability. So that's a second set of things. The third set of things, but people use a lot, is the set of generative tasks. So for instance, in this FDA dataset, people give the model context about, for instance, some FDA report for a medical device, and they ask what's the type of the task, and the model has to actually word by word answer correctly, what is the type of the task. And for instance, in this squad data set, you're given, like, say, the model is given a context about the Titanic, and then asked the model is asked, like, who found the remains of Titanic, and the model has to answer Robert Ballard. So of course, like, there are multiple possible answers. You have to write your evaluator very correctly. So maybe the model sometimes only answers Ballard. You have to also give it the point. So people already have, like, a very mature kind of way of evaluating the models. So those are the so-called generative tasks. So generative tasks are in general, like, much harder than the descriptive tasks, just because the model has to answer, word by word, what's the correct answer to the question. So therefore, like, you can imagine that it has a larger variance in terms of the accuracy if you vary the random seeds. So how to kind of overcome this? There is this very nice work from Stanford and Buffalo called Just Read Twice. So they propose the following: that is, what about I repeat the question twice? Not only repeat the question, also repeat the context twice, in such a way that the model can actually answer such a question, like, more accurately and more stably. But unfortunately, even after this enhancement that they call, like, Just Read Twice, so for instance, FDA2 is the Just Read Twice version of the FDA dataset. But you see, like, the accuracies are generally, like, higher, but you still see this large variance of actually 9% of the accuracy difference when you vary the data random seeds. And maybe the variance is a bit smaller on some other data sets, but in general, like, you see this really large discrepancies when you vary the model random seeds. To sum up, academic scale pre-training is really noisy. So one, you don't want to use the pre-training loss as a way to evaluate the model. You don't want to use the perplexity, because that only captures the model's memorization capability, and it talks less about the model's more complex reasoning skills. And number two is that, yes, you can study the complex reasoning tasks, like the discriminative or the generative tasks, but unfortunately, like, you get very noisy results. So if you think about it, the actual thing that's happening behind is because real-world data is really very skill mixed, and it delays actually the emergent skills to show up. So let me explain. For instance, as you will see actually towards the end of tomorrow's talk, that the models actually will simply fail even the simplest two-hop reasoning. So you can test, any of the models pre-trained in this scale. You can test it by saying that, some random person's name X was born in whatever year, then Y was born in the same year as X, then which year was Y born in? And I can tell you, and I will also show you evidence in tomorrow's talk, that all the models will actually fail in answering this question. No accuracy better than random guessing. So therefore, like, the model, for instance, in this scale of what I call academic scale pre-training, cannot even do two-hop reasoning. And the reason is because, like, the simplest reason is because maybe you don't have enough two-hop data in this, like, 100 billion token pre-trained scale. But kind of a deeper reason here is that even if you have, maybe you're still missing some intermediate skills for your model to actually learn this in a hierarchical way. So for instance, suppose, like, I give you sufficiently many, like, three-hop reasoning data, but maybe not enough two-hop data. Then the model can still learn three-hop reasoning, but at a pretty late and unpredictable stage. This is known as grokking. For instance, what could possibly happen is that you can train the same model, like, twice, but using two different random seeds. Once maybe it learns three-hop, like, pretty fast, but the other time maybe it learns three-hop reasoning, like, say, 3 times slower. So this can indeed happen in practice. And for instance, one of the reasons for this to happen is just because you may not have enough, like, say, two-hop data. So the model has to learn the three-hop kind of from scratch, and then, like, it doesn't, like, the three-hop skill, like, it will eventually emerge, but it may emerge very late and very unpredictably. So therefore, like, the real life data may give you, like, some very high variance in terms of how fast you learn certain skill, and you may, like, very easily see some grokking style jumps in the performance if you evaluate, for instance, the specifically some, say, three-hop skill of a model. So therefore, like, real life pre-training is just very noisy. And how to fix this? This is the main topic of actually this entire work, part 4.1 of the paper. So in my mind, there are at least 3 different ways to fix this. The first way is to do post-training or RL. This is what actually people do a lot in practice. Namely, given that the pre-training data maybe doesn't have enough 2-hop or 3-hop data, then can we inject more such data? And people typically do this in the post-training stage. That is, you can inject more kind of 2 and 3-hop reasoning data, through some RL techniques, and then like continue to train the model from the pre-trained checkpoint, and then to make it behave better and better in terms of deeper and deeper reasoning. So this you can do it, but in the context of architectural research, I claim that this may not be a very good idea, because if in the end you get some good performance, then does the performance actually come from the pre-training, or does it come from the RL optimizer, or does it come from a specific RL objective that you used, or does it actually truly attribute to the architecture design that you used? So therefore, once you bring up this post-training thing into this entire pipeline, it becomes even much harder to study, which architecture design is better. So therefore, I personally really don't like this first approach. I mean, in practice, you should definitely do this. You would definitely do post-training. But if you're a researcher that wants to study architecture design, I don't think it's the right path. So the second path, which is for sure a right path, is to scale everything up, right? If you have enough money. But the issue is that it's very costly to repeat your experiments, especially if you want to do controlled studies. Then how many times can you pre-train a model that's 8 billion, that's of 8 billion parameters, right? Maybe you can't do it much. And that may also give you some misleading conclusions. But we are anyways doing this. So this is our part 4.2 of the paper, in which we are going to scale everything up and discover some very interesting phenomena over there. But in today's talk, I don't want to go there. I want to study if we don't scale up, what can we do? So this is the third approach, and it's actually the main focus of this part 4.1 of the talk. That is to build synthetic pre-trained playground. The beautiful thing about building your own synthetic pre-trained playground is that you have the freedom to decompose this entire notion of intelligence into atomic scales. For instance, if you want to study the model's reasoning depth, then you can design data that have 1-hop, 2-hop, and 3-hop kind of reasoning, in your own format, and you can inject such data, as many as you want. You can make sure that this entire ladder of from 1 to 2 to 3-hop kind of training data are all present in your pre-training data. So you have the freedom to make sure all of this happen. So to some extent, the procedure of building a synthetic pre-training playground is to predict what will happen, after post-training, because post-training is going to, inject eventually this kind of, 1-hop, 2-hop, 3-hop kind of reasoning data. But during the pre-training, typically you don't have it in real-life pre-training data. So therefore, I propose to, build our own synthetic pre-training data to kind of mimic what will happen in this later stage. And once you have, built such data, and you can directly pre-train a model on your synthetic data and see which architecture is a better choice. So this is actually the concept I'm using, that is synthetic pre-trained playground. And there are at least 3 benefits of using synthetic pre-trained playground. Number one is that it's very clean. You can control the difficulty of the pre-training environments. You can actually even separate different skills into different data sets. You can design a data that's rich in reasoning, but not in knowledge. You can design another data that's rich in knowledge, but less in reasoning, and so on. So you can do very controllable experiments. And also you can inject infinitely many high quality data to make sure that all the skills emerge early, consistently, and measurably. So for instance, if you want to build 2-hop reasoning, you can inject as many data like this as possible. And if you want to build like 3-hop reasoning data, you can generate as many such kind of data as possible. You can just put all of them into the pre-training data set and then train the model and see like how much accuracy they get. So therefore, like you have full control over the data, and you can evaluate the model like on those like different levels of difficulty of the data separately to see things very cleanly. So number 2 is that by separating the skills into separating intelligence into different skills, this really enables you to do true architectural comparison. For instance, people say that RNNs are better in knowledge and maybe transformers are better in reasoning, but how exactly and how much are they better in knowledge, and how much, for instance, is transformer better in reasoning, and in what type of reasoning? So by designing synthetic tests, you can actually probe those models, those architecture designs, and see like what is the real benefit of using maybe this architecture design, and what type of knowledge or what type of reasoning is this architecture particularly good at. So those are really the messages that you can discover using synthetic playground, but you cannot discover using the real-life benchmarks. Just because in the real-life benchmarks, it's not only noisy, but only a tiny bit of kind of accuracy change. So how much can you read from them? And real-life data is 2 skill mix. And here we want to isolate the skills and to decompose intelligence into really atomic skills. So the third benefit that I think the most important here is that we can, once you do the synthetic pretrain, you can do rigorous science with what I call mini scaling laws. What do I mean here is that you can not only vary the model sizes like everyone else does, you can also vary the data's difficulties. In real life pretrain, you pretty much only have one data set, right? And you cannot control like the difficulty of the data, because real life data is just whatever the difficulty. But now, for instance, if you want to care about the model's, say, reasoning depth, then you can vary like how deep the reasoning is. You can vary the data's difficulty. So you have really this 2-dimensional kind of scaling law. And you can compile this. You can compile, for instance, 2 different architecture designs. And whenever you see a gain, for instance, like this, you can even quantify, for instance, how much exactly deeper is one architecture comparing to another one. So you can do this kind of quantification using such mini scaling laws very, very cleanly. And very crucially, you can, under this like synthetic pretraining playground, it can allow you to very sharply reveal architectural differences. So in the past, there was only, say, 0.5% gain in whatever, say, HelloSwag benchmark. But now, as you will see actually in this talk, there are ways for you to distinguish, for instance, 2 model architecture designs by this much. Like in one case, it's almost 0% accuracy. The other case is almost 100% accuracy all the places. So this way, like you can, really evaluate the model, the architecture's advantages, like very, very cleanly comparing to the real life data. So this is what I call the mini scaling law. And one thing to really emphasize here is that this is not chinchilla scaling law. The maximum model size I actually need to do is only at most 100 million parameters. This is the so-called like GPT-2 small scale. And actually within this scale, you can already discover some very astonishing kind of model advantages. For instance, like one is better than the other one here. The real reason for why you can do this is because you're not studying like the entire intelligence as a whole, but you're decomposing it into atomic scales. So for each one of them, you have the cleanest data, you have like the infinitely many data, and all like you are left to do is to discover, suppose I only care about this particular scale, then which model architecture design is better. So it allows you to do this like very, very cleanly at a very, very small scale. So this is like the synthetic pretraining playground that I'm going to advocate today. And for the rest of the talk, let's see like how I'm going to build such a synthetic pretraining playground. I'm going to begin by telling you what I think are the most important design criteria for such a synthetic pretraining playground. Number 1 is that I want to design the synthetic tasks to really challenge the architecture's depth. That is, I don't want to like study shallow tasks, like what many of the prior works did. For instance, not to say full copying, but some people study like associative recall or flip-flop. So those are like the tasks that are too shallow, like can be implemented by just one or two layers of a transformer. But I want to really challenge the model's depth and test the model's mental reasoning. So let me explain what this means. So in a transformer or any language model, what people typically do in autoregressive training is that you feed forward the tokens, and for instance, if you have 24 layers of a network, then this is the model's depth dimension. But there's also this time horizon. That is, if you do autoregressive, then you take the output of the previous token and then feed it as the input of the next token. So this is actually the dimension of the so-called system 2 reasoning, also known as chain of thought. But this is the dimension I want to avoid. I want to study actually the model's capability on mental reasoning, also known as the system 1 reasoning. That is, you want to see like if the model can maybe perform a complex reasoning task without writing anything down, but directly spelling out the answer. In Chinese, this is 心算. So some people translate this to like compute by heart, but actually in English, we say it differently. We call it mental reasoning. So we want to test the model's mental reasoning capability, but not the system 2 or chain of thought reasoning capability. So why do we care about this? Because if a model can support, for instance, 4 steps of mental reasoning, and say on top of that, you can also do 8 steps of chain of thought reasoning, then that's a total of 32 steps, right? So therefore, like we want to study this really orthogonally, because in the chain of thought direction, this is really almost not related to the model's architecture at all, because you can just, for any model architecture, you can do chain of thought, right? But what a model's architecture really influences is the capability of the model's mental reasoning skill. For instance, if you have a model that's too shallow, then of course it cannot mentally reason for too deep, right? So therefore, the architecture design is going to influence the model's mental reasoning or system 1 reasoning instead of the chain of thought reasoning. So therefore, we want to focus here. The third thing, as a design criterion that I want to really emphasize, is that let's focus on short context length, such as like 4,000 tokens. So in reality, yes, people care about, say, 1 million tokens at least. But in almost all the cases I can imagine, what people really care about is first to retrieve maybe some relevant information to a local context of, for instance, 4,000 tokens, and then do the reasoning over there, like locally. So therefore, like this is the part we actually care about in architecture design. That is, once you have all the knowledge about this entire context, then can I perform some deep reasoning like inside this range? So I want to explicitly avoid, for instance, studying a model's capability on both long context and maybe some deep reasoning, because that's almost just impossible in all the cases, because very often due to some memory limit, if you're using, say, sliding window attention or RNN, then you can't imagine the model to do a very deep reasoning task on a super long like context. That's in general just impossible. What in the end actually matters is once you retrieve the information to a local context, then can I do deep reasoning in this area? So therefore, like when studying architecture design, I think what matters the most is not maybe necessarily about how long the model can reason. For instance, if it's a long context, maybe all you care about is information retrieval. But in terms of a local context, this is the place where you care about how to perform deep reasoning. And this is like what I want to emphasize at the third point. The fourth design criterion I want to really voice up is that I want to ensure real-world relevance. I want to avoid studying tasks that are maybe interesting, but also on the other hand solvable by external tools, especially like long-digit arithmetics. For instance, you can test like Llama 3, 70 billion, and you can check like even the simple task of 6-digit addition turns out to be extremely hard for it. This is a counterexample you can very easily find out. And for like more modern models like Gemini 3, GPT 5, and so on, you can try like say 6-digit multiplications, and they're going to fail like with very large probability. So this is an issue with all the modern models, but is it worth fixing it? I don't think so, because if on one hand you can increase the model's number of parameters by, for instance, 10 billion, but improving its, for instance, 6 or 8-digit kind of multiplication capability. But on the other hand, you can, for instance, delegate this just to a Python external tool and not to make this like a skill that the model needs to be learned, but saving 10 billion parameters, then I would certainly prefer the latter, right? So therefore, I don't think studying those large digit kind of arithmetics to be important. So those are the 4 design criteria that I think are important, and I want you to also keep in mind. So now with those design criteria, let's see what are the tasks that I'm designing. The first task is what I call task Depo, which challenges the model's mental reasoning in terms of depth. So here is how the task looks like. It starts with a BOS token, and then it's first given a set of n edges that actually defines a random permutation of n nodes. So if I see x1, y1, then that means there's a directed edge from x1 to y1. And all the edges, n edges, is going to form actually a cycle. Okay. Then after that, I'm giving the data, for instance, up to 10 queries, and each query is first given some value integer k, and then a node named q, and the model needs to answer what is the kth successor of this node q in this permutation. So this, if you think about it, is a k-hop in-context information retrieval task. Because, for instance, if k is 3, then whenever you see q, the model needs to figure out where q was in this definition, and what does q lead to. Maybe it leads to this node, and you have to do this retrieval again and again. Like say, if k is 3, you need to do the retrieval 3 times, and then finally put down the answer. That's this node, maybe A. Okay, so this is k-hop in context information retrieval. So during the training, we don't fix n and k. So very crucially, we define some big N and big K, and then we generate data by making k to be sampled from 1 to k and making n to be sampled from 3 to big N. So this way, we ensure we not only have hard data but also easy data. So we have 1-hop data, 2-hop data, until the big k-hop data. We have all the different kind of difficulty hierarchies. So this way, the model can perform more hierarchical learning by first learning the easy thing and then gradually learning the intermediate difficulty skills, and then the hardest, say, the k-hop kind of reasoning, kind of more gradually without grokking. So we in fact provide 2 different data sets. So one we call Depo 1 that has more number of nodes but fewer number of hops. But the other one with a fewer number of nodes and more number of hops. And also very crucially, instead of making each node a single token, which is maybe too idealistic, we made them actually multi-token words. So in the first case, maybe 1 to 2 tokens. In the second case, maybe 5 to 7 tokens. The reason we chose this is because we just want to fit everything into a context of 2048. And you're welcome to generate longer kind of things to test the model's capability on longer sequences, but I truly don't think that's needed. As you will see that within this context length, this type of data is already more than enough to actually test the model's capability on how deep it can reason. That is how many hops it can perform in this multi-hop in-context information retrieval tasks. So that's how the training data is formed. And during the evaluation, we decide to fix n to be just the maximum n, but we vary k. So you're going to see some plots like this in this paper that basically shows you, for instance, how fast does the model learn 1-hop, how fast does the model learn maybe 2-hop, how fast does the model learn 4-hop. And if you see a picture like this, it means the model is learning this reasoning task very slowly. But if you see some picture like this, it means the model is learning the reasoning, especially the reasoning depth, much faster than the one below. Okay, so this is the beautiful thing about synthetic tasks, right? You can really quantify, for instance, how many hops of reasoning model is learning and how fast is the model learning, for instance, a specific hop. So it gives you really visual kind of comparisons between model architectures. So that's one of the main reasons we're using synthetic pretraining playground. But this is only task number one, task Depo, okay, or mental reasoning depth. In the second task, I'm going to test the model in terms of reasoning breadth. Okay, so instead of giving the model a permutation this time, I'm giving the model a directed acyclic graph, or DAG. And I'm going to ask the model that is given a node Q, then what does Q depend on in this graph? And answer in topological order. So the format of the data will be looking like this. So you're given basically a graph with m edges, and then once you're given like a Q, then the model needs to answer, what does Q depend on in topological order? So this is how the data looks like. The reason this is a very important task is because it actually connects back to, for instance, the simplest kind of reasoning skill, even back to the grade school math problems. So we discovered this actually in our prior work. Now, a grade school math problem may look like the following. So Himmel has maybe as many apples as Fern and Star combined, and Fern maybe has 3 apple trees, each producing like 20 apples. Then how many apples does Himmel have, right? If you're like confronted with such a grade school math problem, then for language models, we discovered in our prior work that the model has to mentally pre-compute the topological order of this entire dependency graph. The reason for this is because before the model even answers this question, it has to understand that the number of apples like Himmel has depend on Fern's number of apples. And then the model has to first compute like how many apples does Fern have, as maybe the first sentence of the answer before the model can even answer, for instance, how many apples does Himmel have. So without going to the details, I just tell you that transformers, for instance, are capable of doing this, learning this skill. Like if it's pre-trained, for instance, on grade school math problems like this. And this is a very critical skill that's hidden behind, for instance, transformers regarding like how it can perform reasoning and so on. But that was in the prior work. And in this paper, what we care about is that does the architecture design actually influence how fast the model actually learns this skill of, like, say, doing the topological sort. Okay, and in particular, we decide to remove all the English and only keep kind of the symbolic part. That is, we're given the graph, given basically the graph to the model directly, and then test if it can learn this skill of doing the topological sort. And if you are interested more in like why this connects to the model's reasoning skill, like in grade school math problems, you're more than welcome to look at our previous paper. But suppose now you trust it, then this is a very good synthetic task to use to test the model's reasoning breadth, that I call, because like it's more like a search tree. So in this task Brevo, again, like we are going to use 2 different variants. In one variant, like we're having a larger graph, but each node has only 1 token. But the other case, we're having a smaller graph, but each node has between 2 to 4 tokens. The whole reason for doing so is to fit everything into a context length of 1500. So that turns out to be more than enough for you to evaluate how fast does a model actually learn this task, and how does the architecture design influence the model's capability on performing such reasoning breadth task. And for the simplicity of this talk and tomorrow's talk, for both Depo and Brevo, I'm going to skip Brevo 2 and Depo 2 and only show you Depo 1 and Brevo 1. Just to have to make the pictures clear. But the reason we did it more carefully in the paper is because we want to also showcase the fact that actually those parameters don't matter. What matters in the end is this class, this family of tasks that you design that will help you to distinguish which architecture is better. But actually the specific choice of which what's the size of the graph, or maybe what's the number of tokens, maybe doesn't matter that much. But we still anyways did the 2 for each in these 2 cases. In the paper, you're going to find out that it doesn't matter which one you use, and the conclusions will be similar. So the third task we study is knowledge capacity. So this actually, again, goes back to our prior work, part 3.3. Over there, we designed some synthetic biographies of n individuals. So here, like a random person's name was born in some random year and has some biography like with some randomly generated entries. So what's important in that data is that because it's synthetic, we actually controlled the number of knowledge bits. For instance, if the person's birth year is generated from, say, 200 number of possible years times like 12 number of possible months times like 28 number of possible days, then this is actually a total number of 60.21 bits of Shannon information. So therefore, like if you have a model that is pre-trained on a data like this, then you can actually, even if the model has not fully learned all the knowledge, but there is actually a way for you to quantify how many bits of information did the model learn, did the model actually memorize. But of course, this is subject to like some very careful definition of what memorization means. That's in our prior work. But the key point is that once you have that notion, you can start to do another kind of scaling law. That is, you can vary the model sizes and vary, for instance, the data sizes, and then look at in this dimension, in this vertical dimension, you can look at how many bits of information did the model learn, like per parameter. And what matters in the end is this kind of frontier line that tells you, for instance, here in this case, this architecture family can hit a maximum kind of knowledge capacity of 1.4 bit per parameter. Okay, so this is like the technique we designed in the prior work, part 3.3, and it turns out to be a very good testbed for deciding, how many knowledge bits can a specific architecture family learn. And all you need to do is to vary the model's sizes. But one crucial thing to point out here is that this is not chinchilla scaling law. The maximum model size you need to look at is just at most 100 million parameters. And that turns out to be enough for you to accurately measure like how many bits of information can the model memorize per parameter for this architecture family. And therefore, like you can actually use this to compile different architecture families to see like which one can memorize more bits of knowledge per parameter. So that's the main idea behind the third task, knowledge capacity. So the fourth task we're going to cover is what we call it knowledge manipulation. So this is a knowledge manipulation is a type of reasoning, but it's very different from the first two types of reasoning. The first two tasks I'm defining here were actually in context reasoning because you're not using any knowledge. You're just like retrieving information from your context and then perform maybe a deep or maybe some like a tree type of reasoning. But there's another like very different type of reasoning that is knowledge-based multi-hop reasoning. Let me give you one example. Suppose you asked the question about what is our ex-president's wife's name. So to me, this is a three-hop reasoning question. I have to first figure out, who is our president? Then who was our previous ex-president, right? And then who is that president's wife's name? So therefore, to me, this is a three-hop knowledge retrieval task. But here, in order to really distinguish this from the in-context reasoning, I want to give it a different name. I want to call it knowledge manipulation. So therefore, it's a three-hop knowledge manipulation task. So once again, we want to study the model's capability on knowledge manipulation without chain of thought. So if you remember this picture, because if you do chain of thought, then even if the task is a three-hop reasoning, then the model can just do the three hops like one by one, and then it just boils down to knowledge capacity, right? Because all you need to do is to retrieve the information, retrieve the knowledge like 3 times. But instead, we want to test the model's mental reasoning capability or system 1 reasoning capability. So we want to measure like how deep the model can perform such knowledge-based multi-hop reasoning. So this is the goal of this knowledge manipulation task we're going to design. Okay, so one quick comment actually from our prior work is that we discovered that knowledge manipulation is a very hard task. So the model must learn this skill during the pre-training stage as comparing to the SFT stage. But this is actually good news for us because it means this is a perfect task, a perfect skill for us to test an architecture design, right? Maybe one architecture design is going to make the model learn this skill much faster comparing to a different type of skill, comparing to a different type of architecture, right? So therefore, this is a perfect test bed for us. But how to design, what kind of knowledge manipulation task do you want to design? So we decide to do the following. That is, we want to make this as orthogonal to the previous tasks as possible. So therefore, we want to reduce the model, the task. It's a knowledge manipulation task, so therefore it has knowledge, right? But we want to reduce its difficulty on knowledge and increase its difficulty on manipulation. That is, we want to task maybe more hops on this reasoning thing, but reducing like the amount of knowledge. If you have like the entire word knowledge and do like 3-hop reasoning, that would be maybe too complex, too difficult as a task. So therefore, you want to reduce the knowledge bad, but increase the difficulty on the manipulation. So with all of this in mind, then actually the most natural thing that came to my mind, at least for humans, about knowledge manipulation is the following. That is, for humans, if you think about it, for the simplest possible knowledge is the 9 by 9, say, multiplication table. If I ask you, what is 6 by 9, you're not going to do the computation again, right? You're going to, retrieve this from your memory about what the answer is, 54. And therefore, for humans, this, I really strongly believe, like I'm happy to argue with anybody who doesn't agree, is that I think for human, this is perfectly a 2-hop knowledge manipulation task. That is, what is 6 by 2 plus 7? You have to first compute like 2 plus 7, the answer is 9, and then do like 6 by 9. So if you use scratch paper, you can reduce this to 1-hop knowledge retrievals. But if you don't use scratch paper and think about everything, like do the mental reasoning for humans, then this is a 2-hop knowledge manipulation task. So motivated by this, I think that the best data to actually test the model's multi-hop knowledge manipulation is to perform the following. That is, to ask the model to do modular 23 arithmetics. So I claim the following is exactly a 3-hop knowledge manipulation task for language models, because the model can actually first memorize all of those like 23 by 23 addition, subtraction, or multiplication tables, modular 23. And once he memorizes such knowledge, which is, by the way, tiny, it's not a big table, right? Then the model can start to manipulate using those knowledge, right? Maybe do a 3-hop reasoning, or maybe do a 10-hop or a 13-hop or a 16-hop. So therefore, like we decide to design our task manual or task manipulation to be exactly this like modular 23 arithmetics, but with the length, the number of hops to be either 10 or 13 or 16. So therefore, like that's the 3 levels of difficulty that we use for this task manual. So this is our design for the 4th task, knowledge manipulation. So the last task, the task number 5, I want to design will be completely orthogonal to the previous 4. That is, if you think about it, the previous 4 tasks, they rely on explicit relations. Like it can be like some graph edges, it can be some key value pair knowledge. But in all of such cases, the language structures are explicit and fixed, no ambiguity. If I say like some person was born in this year, then this is fixed, like there's no ambiguity. Like where the sentence starts and where the sentence ends. But now I want to, in the 5th task, I want to test the model's capability like on resolving structure ambiguity. That is, I want to design a task that is as hard as possible in terms of the structure ambiguity, so that the model has to perform some very long range, like global, maybe even hierarchical structure decisions in order to figure out maybe even where was the beginning of a sentence. So this task was actually already designed in our prior work. That is, we actually developed a class of context-free grammars specifically for this purpose. So this is not any context-free grammar. You can use like English context-free grammar, but that would be too easy. So we designed a specific family of context-free grammars that look like the following. So you start, the way for you to generate a sentence is by first starting from the root, then with maybe 1/4 chance, you convert the root into maybe 20, 21, and here like each number here is an intermediate node. Then for instance, for 20, then with like probability 1/3, you go to like 16, 16, and another probability 1/3, you go to like 17, 16, 18, and so on. So if you continue this procedure until the very leaves, then you form a randomly generated sentence. So what's interesting about this context-free grammar is that on the sentence level, you see this sentence almost appearing just like a random sequence of 1, 2, 3s. But behind it, there is a unique parsing tree, like based on this context-free grammar. But it's not really given to you. Like you have to do some actually dynamic programming, very non-trivial dynamic programming to parse like where is the beginning kind of this sentence or this sub-sentence. So I'm not going to give you the too much details about this context-free grammar family of things, but I just want to emphasize on a few things. Number one is that it has minimal symbols and rules. So the rules I already presented to you, like just now, it's like very short. You can describe it very easily. So therefore, it has minimal knowledge. So therefore, it's completely orthogonal to task number 3 and task number 4. And also, it can generate long and highly ambiguous sequences, like this sequence of 1, 2, 3s, right? Like even for humans to parse, what this is, you need at least, I think, scratch paper and 30 minutes. So therefore, like it's also orthogonal to the first 2 tasks, because over there, yes, you also have long sequences, but the sentence structures are very fixed and not ambiguous. But here, like your sentence structure is extremely ambiguous. So that the number 3 is that this really forces the model to perform global structure reasoning, and by like implementing this kind of dynamic programming style of parsing. So the test data that the training data from this task will be just those randomly generated random-like kind of sentences, and we actually created 3 different data sets that we have some, for historical reason, we have some code names, CFG 3F, 3J, and 3K. So they once again have this increasing level of difficulty so that I can do mini-scaling laws. And very crucially is that once the model is sufficiently trained on such like random looking like sentences, by the way, the model doesn't even see what are the rules. It has to learn all of them. And during the evaluation, you just probe the model to give it a starting BOS token and let it just generate freely. And the model is going to generate maybe 1,000 tokens. And in the end, you only give it a point if the model is 100% correct on generating a sentence. Okay, so a randomly generated sentence in general, like will have exponentially small probability to be correct. But here, like once the model, after this pre-training, you check if it can generate only those sentences that 100% satisfy the CFG. So this is our technique to probe an architecture's capability on resolving structure ambiguity and perform this kind of hierarchical structure reasoning. So in our prior work, part 1, we discovered that transformers are capable of doing that. But what's important in today's talk and in this part 4.1 of the paper is to discover, for different model architectures, is one of them maybe faster than the other one in terms of learning those CFGs. And in other words, is one specific architecture design better than another one in terms of learning structure reasoning? So this is what we care about and why we designed this task number 5. And it would be very crucial, like in tomorrow's talk, in terms of distinguishing maybe some, if one architecture is better than the other one in this dimension. So those are the 5 tasks. You're more than welcome to design maybe a 6th one and a 7th one, which I'm not doing right now. But I really hope that one can, if you want to increase to this list, you can design a task that's really orthogonal to all of the skills in this current list. And if you have some good ideas, let me know, email me. But for now, for today's talk and tomorrow's talk, I'm only going to use those 5 synthetic tasks as the test bed to see the model's performance. So for 4 out of our 5 tasks, the first 2 and the last 2, I'm going to color code them using color purple for the reasoning depth and color green for reasoning breadth and so on. So for those 4 tasks, as you have can already imagine, then I'm going to do this mini scaling laws. That is, I'm going to vary the data's difficulty by 3 levels of difficulty and model sizes by 4 different model sizes, maybe 12 layers and 768 dimensions. That's GPT too small, but I can even do it even smaller than this. So this is like the format you're going to see, like with respect to 1 data and 1 architecture. But for knowledge capacity, it's different. As I mentioned, that because you're testing the model's capacity, you have to really do a little more of experiments. But the good thing here is that the maximum kind of model size you need to look at is at most maybe around 100 million parameters. That turns out to be more than enough for you to measure like what is the knowledge capacity of a model, as well as like seeing the model's performance on any of the 4 tasks. So this is like the format of the 5 synthetic tasks. So before I conclude today's talk, let me actually show you at least 1 result that is using this synthetic playground. Then how can we compare, for instance, llama versus linear attention versus Mamba2 or versus GDN? Okay, so here is the result. So you can already like read some very interesting things. So number 1 is that you really don't want to use linear attention. So linear attention performs like pretty bad, in almost everywhere. Number 2 is actually already surprising. That is GDN, gated delta net, and transformer are actually both good in terms of how deep you can reason. But in terms of how the reasoning breadth, then GDN actually performs better than llama or transformer. So this actually explains why in practice, like you can see that in some evaluation benchmarks, GDNs are actually better than transformers. And we actually pinpointed to exactly where this happens. That's in terms of the breadth of reasoning. And in terms of knowledge capacity, you can see that the linear models like all perform like pretty good and much better than transformer in terms of how many bits per parameter the model can memorize. So they're good in memory. And Mamba2 and GDN turned out to be especially better than the other 2 in terms of knowledge manipulation. But finally, in terms of this structure reasoning, then transformer is the only one kind of that works very well. But there's a reason for it, because when doing like structured reasoning, you probably want to know like where this token is. Is it far from me? Is it like close from me? And doing this full attention really allows you to do this kind of positional based computation like more easily. But for instance, if you do like recurrent architectures like Mamba or GDN, you are less capable of doing that. So therefore, like the first thing I want to sum up here is that this synthetic pre-trained playground makes a lot of sense. It matches people's belief, like in terms of maybe which model is better in which skill, but it actually opens things up and to let you see things very cleanly. But a very crucial thing, a warning I want to give you is that this comparison is not fair. So in fact, there is a critical architectural component that is missing inside transformer and GLA or linear attention, but is present in Mamba and GDN. So that actually makes this comparison like underestimated, makes this comparison really underestimating the performance of transformer or linear attention, but overestimating the performance of Mamba2 and GDN. So in the next talk that will be online tomorrow, I'm going to show you, what this component is, and then after, adding that component like to all of the models in a very fair manner, at that point you are going to see a more informative comparison across the architecture designs. So therefore, like this picture only shows you some basics about, this is a good testbed, but it doesn't actually tell you enough information about what architecture you should use. So therefore, like you're more than welcome to attend my next talk. That would be on like using this synthetic playground, then what architecture principles can you derive, and what is this so-called canon layers that we are going to introduce. So thank you so much for your attention, and see you in the next talk.